So what I'm going to be talking about today is ways that we could use nanotubes, but not only nanotubes, a lot of different types of carbon materials to make really cool things that they're not just cool, they're actually also useful. Really, today, if you go around the museum, you'll see a lot of nanomaterials, from nanoparticles to nanotubes, possibly, buckyballs, and a variety of materials. And that's fine. I think the most important things we need to remember is that the great part is when we start actually putting them together to actually make something useful. That's actually not necessarily my idea or anybody's idea. It's actually how nature does things. So, in fact, if we look at the base of life, which is a DNA molecule that is right here, we see that DNA itself is made of nanomaterials. In fact, with just 4 types of nanomaterials, essentially 4 molecules, we can make essentially anything, including our cells. And then up the cells, we can actually make things that might actually be important and relevant, like, for example, a little dog. Now, the idea is, can we actually do something similar? Can we actually sort of take a set of basic nanomaterials and actually scale them up? The answer is sort of yes. Obviously, we are not anywhere close to mimic and replicate what nature does well. But there are some ideas that in the years actually floated around that suggest that that's actually possible. Like you see here, a little electric motor where it's actually hinged by carbon nanotubes across. Or a little nanocar, which is essentially made of 4 carbon fullerene wheels, and it actually moves across a smooth atomic surface. Now, the question really is, can we go beyond this? And can we actually find the right toolbox, the right set of materials that we can use for this? Now, I just want to emphasize here that nano, it's about being small, but not necessarily it's the only important thing about nanomaterials. When we start talking about small things, we think about computers, for example, and we see that we might have, for example, a transistor, which is becoming smaller and smaller, and allows us to actually go from things that are inside a processor, that you have a lot of transistors, these little objects that actually made the computer run. If we make them smaller, we can pack a lot more of them. And so we have, for example, a transition from something like 1.2 millions to 700 millions of transistors. Now, the point is, while we are making things better, it's still a processor, it's still a PC chip. And so it's not something that it's a new idea. Essentially, we are improving on something we already know. So really, it's not just about using something small. We need to use something small, but also a combination of other materials that are actually also small. And in fact, there are lots of things that we can exploit this sort of problem for. And particularly, as it was mentioned at the beginning, there are lots of needs today that need to deal with radical new ideas. Some of them actually have to do with energy, which is what my research actually focuses on. And here I just provide a few examples of what those actually might be. We have, for example, obviously solar cells. We wanted to look into making better batteries. For example, do some hydrogen storage, creating electricity from heat, but also actually improving the way we collect the sun and transform it also into heat. Now, again, I want to stress that it's really important that we focus and actually we make a very flexible and cheap set of nanomaterials that we can actually use for the purpose. And for that, I always sort of take this as the example that I follow through. Now, as kids, and again, I'm sort of a grown-up kid, but I'm still a kid in a way. I love to play with Lego. And so the beauty about Lego is not just the fact that those bricks are actually colored. I mean, that's great. But also, there's a lot of them. And each one has a specific function, and it serves for a specific purpose. Now, the creativity of actually putting them together allows us to create essentially new things. They are the most diverse. So the idea is really that we are trying to explore here is exactly the same. Trying to get the same set of tools that we can use to make new things on a variety of levels. Now, the question again is, what kind of nanomaterials? Carbon is a very promising one. And in fact, here, I'm actually bringing up some examples of what different type of carbon materials exist. Some of them are something very expensive, like a piece of diamond. Some are not, like a piece of graphite. And then there's a variety of nanomaterials that comes out of that, from graphene, which is essentially a layer of carbon, into nanotubes or buckyballs. But again, you can go beyond, and you can actually have things like little wires like this. Then you can make carbon fibers. This is all carbon. You can actually make things like little sponges like this. It's full of just plain carbon. Or if you go really simple, your pencil has a lot of carbon in it. In fact, has a lot of graphite in it. So carbon is a very flexible material by definition. And in fact, that's something that essentially sparked the idea of actually using it for today's application. It's not just really us that actually want to use carbon. Carbon is actually what nature does to run essentially the cycle of life in what is called the carbon cycle. Now, I don't want to go into the details about this, but essentially the idea is that carbon is the sort of a currency of transmission for the way energy is transmitted across nature. So from CO2 in the air, we actually use it through photosynthesis to actually produce fossil fuel and then all around it back again. Now, this is not necessarily what we're trying to do with carbon nanomaterials, but it's to say that really carbon is at play on a very strong level for energy applications. And in fact, obviously, as it was mentioned before, carbon is what we use for energy in the first place. We don't actually use it really smartly, in my opinion, in the sense that we just burn it. It's sort of a direct way to do it. It's effective. We get a lot of energy out of it, but it's not necessarily the only one. And in fact, the question is, can we go beyond burning carbon and actually use it in a sort of a more smarter way? Now, in the next slide here, I just want to point out that it's a sort of a stretch. But essentially, what if we think about taking one barrel of oil, okay, and instead of burning it, we actually make, with the plastic we can make of that, solar cells. Now, can you guess how much more energy we can get through that solar cell, through the life of the cell, rather than burning that oil? Now, if you do that little calculation, it turns out that it's on the order of 10,000 times as much. It's actually a very astounding and incredible number. It's very, very high. Why don't we do it? Well, I'm not going to go into that, but essentially, this offers a lot of potential to go beyond the idea of burning fuel and to actually do something a little bit smarter and to actually make some materials that actually capture better and distribute better that kind of energy. Now, let me go back to this carbon toolbox idea. The idea, again, is to take carbon materials and assemble them together in a sort of a smart way. So what I'm going to show you right now is two applications that we are currently working on in our lab. One is solar thermal fuels, which are essentially based on a carbon nanotube with a specific molecule that I'll talk about in a second, with the idea that we can store solar energy and then transform it later into heat. The other one is all carbon photovoltaic cells. Photovoltaic cells that are made just with carbon. Now, let's start with the first. Why do we need solar to heat conversion? Well, there's a variety of reasons why we want to do that. One of it is, for example, the fact that we want to make, for example, a solar cooker. We are out in the desert. We want to make something warm and nice to eat. We need to have something that collects the sun, so then we can heat it up. But obviously, we want to also do things like heating up water. Or we can actually go fancier and actually make these big concentration solar farms where we collect the sun, we boil some water, and we make steam out of that, which we create electricity. Now, the problem with all of this is that we can only add that once we actually have the sun. There's no sun, you don't have any of those. You don't have any food, you don't have any hot water, you don't have anything. So the idea is, can we actually store that energy somehow, so then once we have that energy stored, we can then release that heat whenever we want. Maybe tomorrow, maybe in a month from now. So that's actually where our fuel actually gets along. So this is the molecule, actually, this is the real thing. You're kind of very welcome to come in later and see it. It's kind of a powderish. So if you actually take a huge, super unexistent microscope and you blow it up, it looks something like this. So this molecule, azobenzene, it's essentially a set of carbon atoms connected by two nitrogens. What it does is essentially it stores energy into itself, and then it can be released at a later time. So for example, when we actually place it under the sun, this molecule, what it does, it twists itself, okay? And by twisting itself, it goes into this sort of state. You can put it there, you can sort of save it for later. You can trigger it, you can activate it, and then once you activate it, the molecule comes back to its original form, and then it releases heat. Now, this is not something new. It's been around for a while. The problem is the time that it will remain charged, it's actually very, very limited, very short. It's on the order of a few minutes. So it's not really usable. So the question is, can we do something better? Can we maximize the amount of energy, but also the time that these things remain charged? And so here, the idea is, again, to take a combination of nanomaterials, try to improve in that. So what we do is we take, again, the same molecule right here, and we attach it, for example, to a nanotube. And you can see that we obtain something like this. Now, by the fact that we packed a lot of these molecules with each other, they work together to collect the energy rather than on a single level. And what that allows us to do is something very amazing to us, and that is to increase a lot the amount of energy you can store. So what that means that, for example, for the pure molecule, you get what we call energy density, which is essentially how much energy can you store in a liter or in a sort of a fixed amount of this material. It's actually very, very small. You can see lots of zeros there. But if you actually put them on a carbon nanotube, you can see that it goes to very high values, very high numbers. In fact, they're very similar in terms of energy density to the value that we get for example, a lithium-ion battery, a battery that you'll find on your phone. So it's actually quite remarkable. But then again, this is one example, and we're actually synthesizing this in our lab, and it actually shows that this is actually working. Now, but you can go fancier. Why limiting ourselves to nanotubes? There's a lot of other materials, other configuration we can explore. And so these are some other ideas that we are trying to promote using different types of carbon materials as our backbone, essentially, that sustains these sort of molecules. Let me move to another, the other subject of this little presentation. Photovoltaics, as we know, it's a huge field. It's getting more and more acceptance, and it's actually very, very well used. There's lots of advantages and disadvantages of different technology that we have, and I'm not going to go into the details about saying which one is better or not. But essentially, I just want to point out a few of the things that are relevant for each individual of these technologies. So the most common one is the one based on silicon, which is actually quite nice in the sense that silicon is everywhere. We have a lot of it, and we can actually make it fairly efficiently. These cells are actually fairly efficient. The problem is you need a lot of it, and it's not flexible. You cannot bend it and make, for example, clothes out of it. There are other type of things that we can do with, for example, thin films. They're much thinner. They're potentially flexible. They're a lot more expensive, and most importantly, they're made of materials that are not necessarily abundant, and besides, some are actually very toxic. Finally, organic cells, they're based on plastics, so in a way, they're made of carbon. The problem is, as any plastic, it sort of deteriorates itself pretty quickly. If you take any piece of plastic and you put it under the sun, you'll see that after a while, it gets damaged, it gets cracky, or it gets opaque, and so it's not really usable. So can we do something similar to what we did with the solar thermal fuels, combining nanomaterials? In fact, we combine some of the same nanomaterials to make better cells. The answer is yes. At least in a sort of a initial stage, we can say that that's actually possible, and it's actually very promising. So what we are doing here, we are combining a nanotube, our friend by now, we're always the same one, and we combine it with a buckyball, essentially. It's a modified buckyball, but it's pretty much a buckyball. So when the sun actually hits on this, the buckyball gets excited. We all get excited. The buckyball gets excited too. What that means is that it decided to be so excited, it decides to give off an electron, and it gives it off to the nanotube. It's so nice and say, look, I have one, I'll give it to you. But then the nanotube say, what am I going to do with that? What am I going to do with that? I'll just release it. And then I'll release it to this piece of graphene that sits up here, and it's kind of lonely. But then again, here you have essentially your negative electron of your cell. On the other hand, the buckyball at the bottom in green here is the same. Without this electron, feels sort of more positive about it. He actually felt like it did something good. And so with that, it becomes the positive electrode. So here's your solar cells, essentially. Now, this is actually what it more like it looks like to some extent. Again, it's a combination of nanotubes and fullerene with graphene electrodes on top. Now, you might say, well, why is that any better or different than what we have already? Well, it is because, first of all, it's extremely stable. Like most carbon materials, besides plastic, they're actually stable in any condition. They actually are, you can actually treat them pretty roughly, and they're pretty resilient to that. But also, they're really thin. Carbon likes light. Carbon likes to absorb light to a maximum extent, so you don't need a lot of material to make it. And it's all carbon. In other words, once you're done with that, you can actually trash it, and it goes back essentially to the same carbon cycle that you had at the beginning. Now, these that I show you are only 2 examples, and there's lots of other things that we can do. And in fact, I'll show you a couple of others real quick, like an overview of them. but essentially the sky here is the limit. One of it is, what we think like naively, but actually it seems to be working, a graphene-based water desalination system. So what if you take a graphene layer, essentially a layer, one atomic layer of graphene, you punch holes into that, and the holes are small enough so that only water, this red and white balls are actually water molecules, they actually go through. While the bigger one, the bigger salt ions of sodium and chloride, they actually stick in the back. Does that work? Well, our modeling actually suggests that it does, and we're actually in the process of actually making the first device that does this sort of process. There's a lot more we can do. What if, for example, we wanted to convert heat to electricity? Before we talked about going from the sun to heat, but sometimes we have extra heat that we don't know what to do, and we wanted to recycle that and to make electricity out of that. Now, a device that can do that is called a thermoelectric device. So what happens is that we can take, for example, a layer of graphene, and we put some molecules on top, so then essentially we have only the difference that we have in the temperature between the two sides allows us to actually produce current. It's a very emergent field, but actually very promising, still again made of carbon. So again, the imagination here is the key. These are only a few examples. There's many others that we can think of. And really the idea is to go beyond just the fact that we see a nanotubes or again, a single particle or a single nanomaterials, but trying to see what we can do with to put them together and to assemble things in a very smart way. So with that, I'm going to leave you with this message here. What is your type of application you can think of? As you go across the floor today, try and think and ask, what can we do? What happens if I put these materials together with that kind of material? Can we do that? Does it make sense? Can we actually get new applications? Thank you.